Today we're going to talk about mobile security. Mobile security meaning anything that's related to smartphones and other kind of mobile devices. And I figured to lighten things up a bit, instead of just me talking about everything, we'll have Luca here, a PhD student in the Hive, but also a very dedicated CTF player who has been looking at mobile environments for the last couple of years, I think we could say, and breaking Android front, left, and center, and also having a slightly more modern perspective on all of these mobile environments. So I would like to hand the microphone over to him so that he can lead you through this class and give you much more detail than I ever could. You know, just hyping it up a bit to make him a bit more nervous.
Can you hear me? Yeah. Okay, hello everyone, I'm Luca Di Bartolomeo. So today we talk Android. We go a bit in depth into the Android security. We're going to talk about the trade-offs that vendors do when trying to secure Android, We're also going to talk about a bit of the differences between Android and iOS. The lecture is going to focus on Android. We're going to only touch about iOS a little bit. I know this is the topic you're probably most interested in. Before I start, I would like to know how many of you are currently running Android, just as a quick survey. Can you raise your hand? How many are running Android? Now, of the people who raised their hand, can you keep it up? Who is running a non-stock ROM, custom Android distribution? We have only a single person?
No, 3.
3 people? Okay. Which one?
I'm running Calyx.
Calyx, okay. You?
EOS.
Okay. And what's the third?
Graphene OS.
Graphene OS, okay, great.
We found the user.
All right, so today's going to be very high level. We're not going to go very much into the details because we only have one afternoon, unfortunately. I could talk about this for 50 hours. Unfortunately, you're stuck in this room with me for only 3. But if you like this stuff, there is a whole course about Android security. It's at that URL you see, Mobisec, taught at Eurocom, and it goes a lot into details. There are some CTF challenges made on purpose to train you guys on Android security. So if you like this stuff, go check it out. Now, before we begin, we need to talk about why. Why do we care about mobile security, right? Now, probably everyone is aware of this, but this was a big change, right? Until 2 decades ago, not everyone was carrying a mobile in their pocket, right? But it's since the 2010s that everyone is carrying a smartphone, right? And the problem with a smartphone is that it centralized all your sensitive information into a single device. So much more than before, so much more than what you had in a laptop, I don't know, 10 years ago, right? And most people actually are very, very scared of their data being stolen / read by. For example, in our society, it's considered very, very much taboo to read someone else's mobile. If you go to the bathroom and you leave your phone unlocked on the table and you catch your friend scrolling through it, that's a massive breach of trust, right? Why? Because we keep so much stuff into the mobile phone. Even for me, if my girlfriend would have access to my mobile phone, I would probably assume it takes 20 minutes before she breaks up, right? And it's not only about personal information, right? Even all our banking today is more or less done on the mobile phone. There are some banks that are only mobile. They don't have a physical office. They don't have a website. They only have an app, right? Now, why is it hard, mobile security, right? It's important why is it hard. Because, unfortunately, on a phone, a bunch of software is running. A bunch of software from a bunch of different sources, right? So first of all, we have the hardware developers and the operating system developers that more or less produce trusted code, hopefully. But the user will then put their data through a bunch of apps made by third-party developers. Very, very commonly, those are individuals. They push their code through those app stores, right? And then you simply install them, right? Now, first big issue is you don't really know if you can trust those third-party developers, right? They can ship malicious code, either on purpose or not. Maybe they were hacked themselves. Maybe someone stole their account and is pushing their code through their Play Store account, right? This is already a big issue, but the second one, even worse, is bugs, vulnerabilities, right? And those affect even the people we trust, the OS developers, even the hardware developers, right? And the security researchers need to look for vulnerabilities and malwares, and also need to check that we can still trust those people. Have they been breached? Even more importantly, when a vulnerability is found, do they update? Do they push code on time to ship patches? And we're going to see this is a massive problem, especially on Android, right? Now, it is important to know that on Android, the malicious code is not exactly the classic one we think of when we have a laptop running Windows and there is a malware, right? On Android, it kind of looks different because the purpose of the attacker is a bit different. The vast majority of malware is done by doing app copycats, where I take an existing app, I reverse engineer it, I decompile it, I add my own code, repackage it, publish it under a different name, maybe similar, maybe with a similar icon, and hope that users install it. You will see that this is very easy to do on Android. Like unpacking an app, adding my own code, and then reshipping, it's very easy. And what do people add? Usually advertisements to make some small profit. Sometimes to steal user data, to sell it to advertisers and make more profit. Very rarely, but it happens, they want to take full control of your device to then maybe encrypt your data and ransom it. And this is much more profitable because people, not surprisingly, are willing to pay for their data because they care a lot about what they have on their phone. They don't want to lose it, right? However, this is much rarer because obtaining full control is much, much harder. On Android, it's expensive. You need a chain of bugs. You don't need a single vulnerability, and so on. There is also another use case, a bit more niche, which is piracy. Some of you might be aware that some of the content you watch on mobile is encrypted, right? It needs to go through DRM, digital rights management. This is the case for Netflix. When you stream a video from Netflix, your normal operating system cannot just read the video file. Or, for example, you cannot record your screen when you're watching Netflix, right? Why is this? Because the Netflix stream is handled by a different part of the phone called the trusted execution environment. I'm not going to go into this because it's a full rabbit hole. But basically, it's a way to protect the content of the publisher, of the vendor, from users trying to steal it and re-upload it to YouTube, right? However, a lot of attackers want to do this, so they attack the interface between the TV and the operating system and stuff like that. Lastly, but probably more worryingly, is political reasons, right? Now, this is a very strong example. But we have to do it because this, unfortunately, is the reality of the world we live in. Government agencies and malicious attackers know that there is so much sensitive information on their phones, and they will use it to their advantage. We have some evidence of this. The most famous case was in 2018, Jamal Khashoggi, this journalist slash political activist in Saudi Arabia. He was murdered, and researchers on the phone, they found evidence of the Pegasus spyware. The Pegasus spyware is a family of spyware. It's property of the NSO, which is basically the Israeli CIA. And they basically realized that he was being tracked by law enforcement, Saudi law enforcement agencies, right? Not only was tracked, they were reading all his chats, they were listening to all his phone calls. Basically, imagine everything in your life is can be looked by them, right? This was a massive scandal. In fact, the NSO later was blacklisted by the US because he also found evidence of them attacking American journalists. It's not exactly clear how the Saudi got access to this spyware. We don't know if it was sold or if it was leaked, and they got access to this kind of leak to run it themselves. So it's all very obscure, but we know that there is evidence that governmental agencies use this, right? And in the vast majority of cases, they do a very well job of hiding the evidence, right? Since this is a software-only attack, you can erase all the traces. And very, very often we should assume that they do, because running an attack like this is extremely expensive. We'll see later more or less what is the amount of dollars required to run an attack such as this, right? And so people usually do not want to be found out. This was probably a mistake that they were found out, so we should assume that this stuff is happening. Main takeaways are two. The first one is mobile security is very important. The second is try to avoid making enemies with a lot of money. But yeah, that's topic for another lecture. So let's begin by some background. We should give a general, we should have a general knowledge of how the Android ecosystem works, right? Because, for example, everyone knows that it's open source, right? Android is open source from the AOSP, Android Open Source Project, made by Google. What not that many people know is that actually a large chunk of Android is not open source. Like AOSP is the base operating system, right? But vendors actually add a lot of proprietary components. Vendors are usually called this OEM, original equipment manufacturer. This means both who makes the CPU, but also, for example, if you buy a device from Xiaomi, they will also add their custom software on top, right? And you can notice very easily, if you buy a Pixel phone, it looks very different from a Xiaomi phone because it's preloaded with all the proprietary beneficial software that very kindly Xiaomi adds on top of AOSP, right? Not only that, Google themselves actually add a bunch of proprietary software. The most famous is the Google Mobile Services, also called Google Play Services. Those are the ones that let you do almost anything on Android, like, for example, have a Google account, watch YouTube, use Google Maps, and so on and so on. This is, for example, a huge issue in the custom distribution community in Android, because Play services are normally not supported for something that Google did not approve. There is a whole design document you need to respect that normally vendors do respect, that tells you all the rules you need to comply to make Play services run on your phone. Tells you, like, for example, the display must be this size, or your battery needs to report the correct percentage, and so on, right? Now you start to see that the amount of code you cannot look at is not that small, right? Starting from the fact that most of the CPUs are ARM nowadays. The ARM part is actually open source. You can read the ARM specification. But then the actual implementation of the chip, not so much, right? It's not easy for you to know what the chip is doing, right? And even worse than the chip, the drivers for all the hardware that is going to run on your phone are also proprietary, right? If you use a Qualcomm Wi-Fi chipset or a Bluetooth SoC on your phone, the drivers are going to be closed source, and they're going to run with kernel privileges. They are a huge attack surface that have been exploited in the past, very, very often, right? And then there is what we were talking about before, the customizations from the vendor. For example, every Samsung device comes pre-installed with a bunch of stuff that actually most of the time you cannot even remove easily, right? Unless you flash your device, right? If you want a more specific example of this, you could, for example, ask yourself a question, I would like to know exactly how does my device verify the PIN I put when I want to unlock it. A very security critical part, right? Unlocking the phone, right? Now, normally the steps you would do is that you would figure out which Android version you're using, then link it to the given AOSP release. You need to figure out which component is actually takes care of verifying the PIN, and then read the code until you find what you're looking for. Now, in this reading the code part, here we have some links to, for example, look at the code, and you will see that, let me open it, sorry. Yeah. This website is the Android code search, and here you find all the code in AOSP, right? We're not going to go through this because it's massive, but if you actually go and look at this is the file for changing the login password. If you actually look at this, you will quickly notice that the open source part stops kind of quickly, right? You see that there is this stack, at which point we encounter this HAL part, stands for hardware application layer, and you will see that the actual verifying is done in this trusted execution environment part, which was the same that Netflix uses, for example, and it's proprietary. You cannot do anything about it. You cannot debug it, you cannot read the source code. It has been reverse engineered many times, but you cannot really look at the code as it is, right? You only know this HAL part, which is the protocol through which your operating system talks with it, so you know that it's sending a request to verify a specific password, and then this magic black box tells it yes and no. And this part is closed source, right? And you'd be surprised for how many components it is actually like this, right? Another thing is that Android is very fragmented. There are so many versions going around. Here on the right, I don't know if you can look, it's a bit small, but you can see that the market share is kind of split. Most of the people are on Android 10 Plus, which is 5 years old. But keep in mind that those versions change a lot between themselves. If you go through the mobile security course, you will notice a deep dive on what changes each version. And the problem, why is it so many people are running an outdated device? It's because companies actually, most of them, stop pushing updates after 2-3 years, which is relatively short. We'll see why this is a huge issue, and why do companies do that later? Why is it so expensive for them to support a device for many years, right? Now, if you're a developer, you need to pick which version to target your Android. If you ever had the experience developing Android apps, you know that there is this variable name in your project called min target SDK, in which you say, okay, if you're running less than this, then your device is not supported. This is an important decision you have to make, because newer versions are more secure, they have more features, and so on, but you get less users, right? It's an important trade-off. Imagine you're a bank, you want everyone to be able to access it, right? At the same time, you really want it to be secure, right? So it's not an easy decision, you need to take it on a case-by-case basis. It's also made harder by the fact that people are still selling very old devices. Like this was on sale on Digitech today, and this is running a 5 years old operating system, right? Which is already out of service by 2 years from CAT. So yeah, people are being sold vulnerable devices from day one, right? In fact, fragmentation is sometimes considered one of the major challenges in security by Android. Why? Let's go into this issue of why companies do not update phones, right? So imagine you're a security researcher, right? And you find a bug, you find a bad bug, something in the kernel, something terrible that affects every single Android device, right? So what you do, you immediately report it to Google. Report it to Google, maybe you're hoping for some money, but in the meantime, you go through their reporting platform, right? And you do this kind of thing called responsible disclosure. You probably for sure heard about it, right? Those 3 months wait period where you give them time to fix the bug, and after those 3 months, you can go on Twitter and claim, I broke this, and this is the exploit code, blah, blah, please give me likes, right? Google in those 3 months rushes to make a fix because the bug is very important, right? And as soon as they're done, they will publish a patch, right? They will update AOSP with a very urgent security patch, and they will tell all the vendors, Xiaomi, HTC, and so on, guys, please update. And here is where the issue comes. All those vendors are almost never running stock AOSP. They're always running a fork because they wanted to add some features. They probably wanted to track users way more than you are normally supposed to, so they have their own modifications, right? What are the dangers? Is that if you ever worked on a fork, on a GitHub project, you know pretty well that sometimes you can just git pull, git rebase, and you're done. Sometimes not. It's going to be very hard to merge the upstream changes with your own, right? And on something like AOSP, this is incredibly worse because maybe Google, to patch your vulnerability, decided to, for example, remove a certain feature. This could happen, this happened in the past, and maybe your Android version was relying on the feature. So now you have to rewrite a bunch of code, and you need to do it fast, right? Because you know that in 90 days the guy will publish the exploit code, or at least tell everyone, look, this part is vulnerable, so hackers can quickly figure out and exploit themselves, right? This is the part that is incredibly expensive, right? Because if you're Xiaomi, you have maybe, I don't know, 50 different phones you're selling, each one with different, very slight differences, and you need to update all of them, right? And you really cannot do a mistake. You're going to push a broken update to phones. People are going to be extremely angry, right? People rarely want to install updates, and if they install update and stuff breaks, they're going to be extremely angry, right? So you cannot mess this up, right? And this is why most companies only support devices for 2-3 years, right? Because it is expensive, because the environment is fragmented, because before a patch arrives to the user, there are so many people and bureaucratic processes that needs to go through, which makes the whole process hard. Now this thing is improving. For example, there is Project Treble. The aim of this project is to define a common interface in which who modifies AOSP can clearly define the parts that are changed, so that when there is an update, it's going to be much easier for them to rebase their version and update it to the most relevant security patch. And this was added in Android 8. So it's being used more and more and more. However, it's still not solving the issue, right? Now, it is important to note that not every company does this. For example, Google actually gives you support for up to 7 years. If you buy a Pixel 8 now, you will get support up to 2030. Right? Which is not bad. You also should note that Google, of course, has an advantage because they are the developers of AOSP. So for them, doing this rebase process is incredibly easier than to other companies, but they're not the only ones, right? So it is slightly improving this issue, but keep this in mind. This is one of the most direct ways people get hacked, because they are running something a vendor does not support anymore. The phone is a bit old, doesn't get the patches, right? Now, as a security researcher, you will look for the kind of problems we mentioned before, malware and vulnerabilities. When you find them, you're going to report them, probably to the bug bounties programs that vendors have, right? Some don't. Bug bounties are when you reward someone who finds a bug with some money. The issue is that most bug bounties have a scope limit, right? They only accept certain kind of bugs, right? Attackers do not care about this. Attackers only care about running code, right? So while bug bounties are strongly improving the field by incentivizing people to report bugs as early as possible, they're still not solving the fact that, for example, attackers are targeting very weird parts of your phone you never thought they were vulnerable, like, for example, the Bluetooth driver, right? Which very often no one looked at before, right? If you are in the jailbreak scene, you saw that some recent exploits on iOS are going through the GPU, right? Which was a very unexpected path, and now Apple is scrambling to fix it. But yeah, this is an issue with bug bounties, right? Okay, cool. Now let's talk about Android apps. I am assuming that a bunch of you guys will have developed their own app, or at least played around with Android apps, right? So there is going to be the basic knowledge that they are made in Java, right? Actually, apps are written in almost every language you can think of, right? While the majority are for sure written in Java, you'd be surprised how many are running native code. By native, I mean C, C++, right? For performance reason. Now, recently, also a lot of apps are written in Kotlin, but then there is Rust. There is almost anything. You can write Android apps without a single line of Java. Most games are like this. They are just written natively to gain a bit of performance, right? How do they communicate with the rest of the operating system and the other apps? Through this API called the Android SDK API, or the Android API reference. There's a lot of names, but it's basically a huge library you can use. It's included by default, and basically you can, anything you want to do with the phone and with the hardware kind of goes through that. Even if you want to open a file, you want to open a network connection, and so on, right? It's very similar to the Java SDK, actually. We'll see some examples. Something you need to keep in mind that this thing is massive. The size of the documentation for this API is huge. And as you will see later, most people actually recommend just searching on Stack Overflow for a relevant example, or directly asking ChatGPT, actually. Some example of the API usage is, for example, I want to do a GET request to a URL. This is exactly the same as in Java, right? The input stream, the HTTP URL connection, you will do exactly the same as in Java. There's a lot of custom Android stuff. For example, the logcat stuff, where you can log messages to the system log. This is an Android thing. You can do info logging or error logging. A bit more complex Android thing would be, for example, if I want to have access to the location, right? This is how you do it in an app. You would register a location listener, right? That then would send a toast, which is the very classic Android pop-up. For sure, you saw it many, many times, the white on black text, which tells you, oh yeah, for example, your location changed, right? This is how you do it on Android. For whoever developed an Android app and ever went on the website for the Android documentation, they know really well how massive maze that is. And so yeah, those are our recommendations. Just go on Stack Overflow directly. An important thing to remember is that the package name is a fundamental thing in an app because it's the unique identifier. It's the, for example, for Chrome, that's the com.google.chromium or Chrome package. You've seen this for sure in Android. The important thing you need to remember is that they are very, very similar to Java packages. If you ever developed a Java application, I don't know if you're old and did this, you'd see that they have the same structure. And this is used to find libraries in the class path and so on and so on. Android gives a bit more importance to this because they require this package name to be unique. Even the Play Store indexes apps based on their package name, right? On an Android app, you're not going to find a main function. There's going to be a set of lifecycle functions. We will see them later. The vast majority of apps are based on some GUI thing. In fact, the Android API gives you the basics, like it gives you the field to edit text, the buttons, all the basic components, but the vast majority of apps just roll their own GUI stack. They use, for example, native libraries to draw directly on screen without using the API. And they don't support any kind of other input than the user touching themselves on the screen, right? The Android API is very, very, very event-driven, right? And this is what we mean by the life cycle. Also, we saw an example of this with the location listener example before, right? You subscribe to receive information that might happen in the system, right? When the GPS changes, a function in your app will be called. Most of Android app development is thought about this process, right? That I receive events from the system and then I do stuff based on that, right? Now, to understand apps, we also need to go into a bit into the details of the 4 components an app is made, right? We have those 4: activity, service, broadcast receiver, content provider, right? Now, each of those has their own life cycle. By life cycle, I mean there are some callbacks in your app which are required. For example, on create. This function will get called when the user touches on the app icon and the app starts. There is going to be on pause, which is going to be called when your app gets sent to the background because the user is switching up, right? Maybe you want to do some stuff. There is on destroy, for example, when the user kills your app, and so on and so on. Everything in your app needs to follow this kind of mentality, right? I could be paused anytime, right? And I must not break. I will go very quickly over all 4 of those, just to give you an overview. Why we need them, you will see later. Activities are a very simple explanation of what activities are. You can imagine them as a single screen of your app, right? It's not exactly like this. An activity can have multiple screens, can be dynamic, and so on and so on. But usually, a developer encodes a single functionality of an app inside a single screen, right? For example, if you take the Reddit app, when you're scrolling your feed, that's an activity. When you want to create a new post and you have a different screen to edit the text, add links, and so on, that's a different activity, right? This is a different process, right? And apps have a lot of activities inside them, right? The important thing to remember about this is that activities can be called by other apps, right? I can, for example, start the mail app with already the activity to compose an email to someone there without going into the menu of to read emails. For sure used when you share something via email, you already get the screen. And this is how it works, right? Because the mail app has different activities and you can choose what to launch, right? Services are more or less the opposite, are what runs in the background, so it doesn't have a screen, right? And there are so many. A very, very easy example is, for example, Spotify. When you're playing something, it's running in the background. Sometimes you have notifications visible. And also this has a life cycle, right? You can kill the music playing, you can put it to stop, and so on, right? And very often, almost always, you don't have an interface to directly interact with them. There needs to be an activity that talks with them. Broadcast receivers are instead what listens to system-wide events, right? For example, when your phone gets plugged into charging, your app might want to do something different. If, for sure, you've used this when you need to enter 2FA into a website, right? And your keyboard automatically suggests you the SMS you received. That's done through a broadcast receiver that listens to all the SMSs you receive and tries to figure out, oh, maybe this is a 2FA code, right? Lastly, we have content providers. Those content providers are basically the way that apps share data between each other. This happens all the time. Whenever you want to share something, you want to have the list of contacts that you have saved. or you want to have access to the calendar events. Even more often, you want to know which settings are turned on a phone. And for this, you need to specify an API through which other apps can do queries to you, and you're going to reply with the required information. Almost always, this is an SQLite database stored somewhere, and you're just going to return the answer of the query. It's just done, right? And all of this you can specify when you make the app. You can specify how this works and how other apps can call you, right? How does this though calling work? How can I send information from an app to each other? And this is where we get into the core part of Android, which is intents. Intents are a very, very custom Android thing, right? You will not find them in other operating systems. It's a fancy word for an IPC message for inter-process communication. And this is really what is the bread and butter of Android. Every time two apps communicate, it's via an intent, right? For example, when you are writing an email and you click a button to attach a file, and you open the file picker, you send an intent to the file picker activity asking for the user to pick a file. Then the user will pick a file, and the file picker will actually reply to the intent with the contents of the file. Right? Same for the browser, right? When you want to open a URL, you don't know what browser the user has installed, so you can send a broadcast intent to the browser view, right? And whoever registered a broadcast receiver for the browser intents can then receive it, and their activity will be started, right? Of course, there can only be one receiver for the browser, but this is more or less how it works, right? Same for the take a picture stuff. When you're in Telegram and you send a picture to someone, that's the camera activity starting up, right, and replying to the intent. Last thing I will show you before we go into a break is the manifest file. This is the most important file on Android app because it basically has a big summary of all those components I told you before. Every activity, every service, every broadcast receiver, or even any intent the app might send must be specified in the manifest. The manifest is an XML file, it's human readable. And now we are going to have a 15 minutes break, and then we're going to look at an example of the manifest file and how does it actually look in practice. Okay, so can you see my screen? Yes. I'm gonna go full screen. Yes. I need to open a new tab and go. Let's download an APK, right? Yes, I can full screen this way. Yes. Let's go on an alternative store because the Play Store. It kind of sucks. Let's download, for example, the most used app I have on my phone right now, and let's look at the manifest there. So we download it here, APK. All right, this is a huge app. It's going to be 200 megabytes. I had hoped connection was faster here. It doesn't matter. We're going to go through a bit more content in the meantime. We're going to see the manifest afterwards. Now, one thing I wanted you guys to know is who made an Android app before here? A bunch of people. How many of you did use Android Studio? How many of you enjoyed the experience? Right? So Android Studio is what people tell you you should use for making an Android app, right? Why? Because it gives you all the stuff prepackaged, right? Syntax lighting, the go to the function declaration, stuff like that. It also gives you all the environment you need to make an Android app. So you know you need a specific version of the SDK, a specific version of the NDK, the native development kit. You need to manage the emulators with this AVD. It's all very confusing. It has plugins if you want to install them. So it's kind of a ready-made setup for you. However, it's not really unknown that everyone hates it, right? It's a hog of memory, it's incredibly slow, no one enjoys the experience, right? Now, since you guys are students of the masters at EPFL, I would like to tell you that you don't need Android Studio, right? You can compile your app from the command line. And I know you're looking at me weird, like, oh, this is a terminal guy. And my answer is it's not really that much more work than compiling via Android Studio. There is a binary called this gradlw. You just type gradlw build. You will need to set a bunch of environment variables and so on. However, the difference, if I can describe it in an image, would be kind of like this, you know. You need to put in some work to be comfortable in the command line, but it's going to be so much better in the long run. You will thank me in 2 years after you figure it out. The fact that you have 8 gigabytes of RAM free on your laptop is going to feel very refreshing. Even the emulators, you can run them from the command line, and it's actually more intuitive. So I would recommend don't fall into the temptation of not looking into the low-level details. Open the hood of your car, look what's inside, understand how stuff works, right? You're going to get faster in the long run. It's not time wasted to know how does actually Android Studio compile an app, right? Can I figure it out and script it myself, for example, right? Now, let's see if we are done with the download. No, wow. This is terrible. We're going to look at the app security in the meantime. That is fine. Give me a second to set this up. Here. Interview. No, wrong one. Yeah, thank you. So this will be the main meat of this lecture, right? The main content. How do we make something secure, right? How do our apps separated from each other on Android, right? Android takes a very straightforward solution on how to separate apps. Each one has its own Linux user. You probably know Android is based on Linux, right? The kernel in large part is the same. There are big differences, but the core functionality is the same. On your laptop, you probably have only a few users running, your user, root, the printing caps, the printing user, a few more. Your phone probably has hundreds of users. Each app has their own. You can set it up so 2 apps have the same user, but as you can see, this is a very, very almost for free way of separating the apps so that each app can read each other's files, right? They can look at each other's processes and so on, right? So the kernel gives you the separation out of the box. And in fact, when you install an app, Android will create a new user, create a new directory for that user, and store all the files there, right? And no other app can access it. This is very enforced, usually. When you look at the software stack of Android, usually you see this image, right? This is taken from the official Android documentation, right? At the top, there is applications. That's the user space code, what the developer writes, runs there. The green, the Android framework, is the API we are talking about. Then there is whatever runs the apps, right? Which is the Dalvik VM in orange, which is basically the same thing as the Java VM, the JVM. Then along the JVM, there are a lot of native libraries that are running on your phone. Almost anything that interfaces with the hardware is going to be written in C, C++, right? And then before talking to the kernel, you usually have this layer, the HAL, right? Now, apps live in this blue space, and they're separated by this having different users scheme, right? Who enforces this separation is the kernel, right? Everything above doesn't really enforce this separation, right? The security boundary is here. Why? There is a specific reason, because actually, if you go deep enough in the Android rabbit hole, you will figure it out that all this stuff is actually not needed. You can write an app that doesn't use the Android API, that is written natively, it doesn't require the JVM, and just performs raw syscalls, right, to the kernel. Why do you want to do this? For two reasons. The first reason is for performance, right? Some games are written like this. They don't want to open a file through the Android API. Maybe they want to load a given level in a specific way, so they need the fseek system call, right? They really need to manage their own file descriptors at a very low level to guarantee the best performance, right? They don't care about the JVM at all. However, this is kind of rare. The most popular use case is malware. Malware is going to do this. Malware is not going to be written in the JVM, it's going to be written natively, right? Most malicious code. Why? Because all of those layers make it very easy for researchers to add like login prints or debug them. At every step of the interface, you can insert your own code and see, okay, I want to study what is this app doing here, right? Every time the app creates an object HTTP URL connection, you can go change the JVM and have this printed every time, right? So malware developers are interested in making this as hard as possible. So the only thing you can actually log and debug are syscalls, right? And syscalls are hard to figure out. From looking at the trace of the syscall trace of an execution of an app, it's kind of hard to figure out what is going on in the app. Much harder than logging at the API level, right? If you ever used a tool called ltrace, you probably know the huge difference than there is in looking at the log of strace. Ltrace logs library calls. It's very easy to figure out what an app is doing. From strace, it is really not, right? You really need a lot more reverse engineering to understand, right? Now, this boundary between user space and kernel, those are what we call syscalls. This is a very, very common concept in operating systems. Even your laptop constantly does them. All the interaction you do with anything in your operating system needs to go through a syscall, and the kernel then decides if the syscall is allowed, and if it is allowed, what to reply, right? So the main security boundary is here, and under it is the same. We have this user space and this kernel space. It is important to realize this. The JVM is part of the user space. It's on the kernel, on Android, okay? Now, another nitpick, well, not a nitpick, an important thing to keep in mind is that not all apps are the same. We have some apps which are different. They're called the managers, right? And they have more privilege, right? We're talking about, for example, location manager, which gives you GPS data. Those apps, the kernel knows them, and the kernel knows they have the required privileges to access raw GPS data, right? GPS data is going to be denied to everyone else that does a syscall to try to get this data. And they're considered privileged apps in Android. So let's take the example from before when we were looking at the location history of the device. If I, for example, call the API function get last location, right? We're going to go into the Android API, And if we look at the code that, if you're curious, is on that link, if you look at the code of the Android API, you will see that this is basically a stub function that will just call location manager service get last location, right? And this will send a request to this manager running on Android, which takes care of giving location data to apps, right? That's the only purpose, right? How do we do this call? You might think it's an intent. Actually, it is not. It is a thing called binder, right? It's another custom Android thing. It's implemented as a kernel module, so it's an extension of Linux. And basically allows for remote procedure calling, right? You should think as intents as more of one-off thing. Like, for example, I want to share a file with someone. This is going to happen every once in a while. I want to open an URL. It's not extremely performance critical, right? Binder is much more lower level. It's going to be much faster. And it also allows for communication in a client-server kind of way, right? So I can really get a lot of data from another process, right? And this is more or less how it looks like in a graph, right? The binder driver handles the communication between two processes, where one is privileged and one is not, right? You can also have communication between two non-privileged processes, two privileged processes. In this example, we have the location manager, right? This communication is handled by something called the Android interface definition language that specifies the protocol of this client-server style communication. If you need to talk with the location manager without using the Android API, you need to follow this, right? Why is this important? Because an absurd amount of bugs were found in binder replying managers, especially if you don't use the Android API, so the standard way of querying those managers, but you write your own way of communicating and you send garbage data. It's basically every year there are tons and tons of vulnerabilities found in this. Now, for who knows Linux, this is under the hood is basically an IOCTL syscall. In Linux, this is a very, very generic syscall. It's basically the syscall used to talk to a driver. Android exposes this device called /dev/binder, in which you can perform an IOCTL syscall and ask for pretty much anything. This is why it's also so vulnerable. This is the same as all the IOCTL vulnerabilities in Linux. iOS has the same. There is this IOKit kernel module, in which for many, many years, almost every jailbreak was targeting it because, again, the attack surface was enormous. It was a very generic syscall to query drivers, right? The amount of managers on your phone is much higher than what you think. If you want to list, you can just run the service list on your Android terminal. You will see this command ADB shell. For who developed an app, it's going to be very familiar. ADB is a tool to interface with your phone or emulator. It has many functionalities like installing an app, copying files, or even spawning a terminal. And with service list, you can get a list of those managers, right? Now, another critical part of an app is permissions, right? The permissions are required to do pretty much anything on Android. Over the years, they exponentially grew. There are so many. Even opening a single internet connection requires a permission. You need to specify in your manifest file, oh, I'm going to use the internet, right? Now, some of those are given by default. Some of those permissions are the operating system will just allow them by policy. Many of those, though, require user interaction, and this for sure you encountered an app that wants to access your pictures, wants to access your camera, and so on and so on and so on, right? And they require the user approval, right? every distro can kind of customize what requires user approval, what does not. So this is all very configurable. Examples of permissions, as we saw, internet, but the list is absurd, right? Even reading the calendar, accessing not even the file location, but the course location, which is not using GPS, but just uses secondary data, like for example the cell you are connected to, or the Wi-Fi stations you see. You can determine more or less your location from there. Even setting a wallpaper requires permission, right? Now, hopefully by now we have the APK downloaded. Yes, it should be. So let me set this up, and yeah, I can show you. Perfect. All right, there we go. So go here. You see? Barely, but you probably can. So we're going to use this this tool. I'm going to introduce later. It's called JADX, right?
Does it make sense to increase the font size? Or is your terminal too advanced?
Almost. I just updated it a week ago with this functionality. So we downloaded an X APK. This is just a different way of packaging an app so that all the data is included. Years ago, you had to download the OBB data separately, and so on and so on. Now it's all packaged in a single thing. You will see that actually, I can even not use JADX. The X APK is just a fancy zip file. In fact, unzip will happily uncompress it for me, right? But some of these files inside the APK have some custom compression, so JADX is just very, very convenient to explore this. Now, JADX is also a decompiler. It also tries to give you the Java source code the app was written in. We will see this later. It will take a bit to open this because it's a 200 megabyte app. This is more or less the norm now in Android. Apps are huge, right? Because phones became very powerful and developers stopped caring for performance and just forcing people to buy the latest iPhone to be fast. Now, when we see the files appear, means we are done. What we're looking for is in the resources, right? Now, here you see why the package name is important, right? There are resources for many package names. What we care about is only the main one, com.tinder.apk. Everything you open is going to be massive. Android apps are incredibly complex nowadays, but here is the manifest. Yeah, you can see. So this is just an XML file, right? Immediately you see the permissions Tinder is going to use, right? Many of them are custom. You can define custom permissions. For example, so I don't know what this Tinder maps receive is, but this vending billing is very easy to assume it's for payment, right? The Tinder app is might ask the user to pay something, and it's going to use the default Android payment processing thing. But we also see that it's going to ask for internet. Internet is something you need to ask for, right? It also asks for permission to vibrate. It also asks for permission for Bluetooth, right? So we don't know, of course, what it is, but you find all of this in the manifest, right? Here we find some intents. Those are the intents that the app might query and ask for the OS, right? For example, here we have an intent for the category browsable action view. What do you think this is? Anyone has an idea? What is this? What is the browsable view? What is this going to call? This is very easy, very easy. You can actually guess it from here. Yeah?
Just opens a browser page?
Yes, yes. This app is telling Android, I might fire an intent to open the browser. Only for HTTPS though. And you see there are many, many other, there's going to be, on any app, there's going to be so many of those, right? Let's go below. Here we find the receivers. Those are the broadcast receivers we were talking about before, right? So this Tinder app is listening on system events, right? Which one of those? They are specified by filters on intents. Also, system events are sent via intents, right? And you can specify which intents you want to listen to via those kind of filters, right? What is this filter going to be? Anyone's guess? This is harder. Install referrer. What is this about? So this is when you actually install an app via the package manager, which is basically always, right? Tinder is going to get notified. Why? I have no clue. I really have no clue. Maybe in the past they had a bonus credit if you install a game or some stuff. Many apps use this for advertisement, right? They want to know if you actually installed whatever they wanted, right? There's going to be so many more. Here now we have the activities. Here, for example, we have the main activity. This is one that's going to be run when I click on the Tinder icon. Main activity is the special name. But of course, there are so many. There is an activity for, I don't know, theme.gif. This is probably, I assume, to display a GIF. They have their own activity. Toolbar chat, and so on and so on and so on. Right? Keep in mind, it's not forced to be a screen. It can be multiple screens, it can be part of a screen, right? It's more or less up to the developer to decide what an activity is, right? We scroll down, this manifest is pretty huge. I don't know if there is more interesting stuff we can find here. We already saw receivers. Yes, we also find a service. This is what is going to be run in the background. And here I actually have no idea what is this about. It's the first time I'm looking at this. So, but with enough time, you can probably figure it out, right? There is some push notification stuff, and so on and so on. So, as you can see from the manifest, you can figure out quite a bunch of stuff. We're going to go back to Tinder later on. Let me go back to the presentation. No. Yeah. Okay, so, sorry. Okay, never mind. An important permission I wanted to talk to you guys about is the read-write external storage. Some of the older folks in this class might remember prehistoric times where we had an SD card in our phones, right? That was wild. You could actually pass files around, right? Some of the crazier people even used cables to switch files. Nowadays, people usually the main way to share files with your laptop is by sending messages to yourself on Telegram or sending emails to yourself. But before, you actually had a USB cable, right? And you had this SD card folder on Android, right? And on some phones, you even had this hardware switch that, when toggled, would basically make the SD card accessible directly through USB, so your laptop would think it's only reading an SD card, right, and not know there is a phone in the middle, right? We still have this folder nowadays. It's all emulated now. Of course, you don't have a real SD card, right? But if you plug your phone to your laptop, your phone will run some code that makes it look like there is an SD card, right? It makes it look like there is a VFAT file system. It's formatted as VFAT is an extremely old file system format, extremely slow. However, it is supported by every operating system, Windows, Linux, and so on. And you guys will recognize some of those folders for sure. For example, DCIM, this is where your camera will store pictures. Downloads folder, this is where your browser will store the downloads, right? And there are some very old ones like ringtones. This is a relic from the past, of course, right? Now, why is this SD card important? Because a lot of apps use this to share files with everyone. So before we saw the content provider, which allows an app to reply to queries, right? But someone else needs to be aware that you are installed, right? Instead, for example, you are the browser, you download a PDF, and you pretty much want anyone to open this PDF, right? You don't care which apps are installed, and you don't want those apps to be aware that you are a browser that downloaded these PDFs, right? So that's why this is the existence of this special SD card, right? It's like a folder where anyone with this permission can store or read files from, right? No matter what is the user, right? Now, we go into the part where we look very, very, very shortly on how would you reverse Android apps. We're going to go more in depth into this on Wednesday in the exercise session, where we're going to look at some simple apps and some challenges around those. But however, on the high level, you should know that apps are made of Java or Kotlin source code. It gets compiled into a jar file, right? This jar file gets then translated into this Dalvik bytecode called DEX. That's what the Dalvik VM executes. There are some differences, but basically those bytecodes are more or less interchangeable. It's not that different from the Java bytecode, so you can safely assume they are the same. An important part is that instead, C source code doesn't go through all this process at all. It gets directly compiled to a shared object, like you would in Linux, right? It's compiled in a different way. You cannot run Linux binaries on Android, vice versa. There are differences in the libc and the environment and so on and so on. But it still looks like a Linux binary, right? As we saw before, APKs are just zip files. You can unzip them. The stuff you should look for is a manifest. The classes.dex is the Dalvik bytecode. The resources, where every app stores its assets, the images, the sounds, and so on and so on. All those are compressed, so usually you don't want to just unzip, you want to use a tool like JADEX that uncompresses everything to you and gives you in a nice format you can just display. This is more or less how it works, right? The important part for you to know is that apps have both this Java side and this native side, C++, which can talk to each other, right? And they are independent. The Java does not need necessarily the C part, and the C part does not necessarily need the Java part, right? When you want to decompile an app, there are a lot of tools available for you. JADEX, the one I showed you, it's probably the one I would recommend the most because it's free, open source, and it's very actively maintained. There is JEB, something considered better, but it's expensive, it's commercial. Bytecode viewer, then who's used to Ghidra? Ghidra recently added support for APKs. You can also use that. In general, Java bytecode is very, very easy to decompile, right? Let's, for example, look a bit at how the Java bytecode looks like, right? So we're still in the Tinder app. Let's close the resources and we go into the source code, right? Now, each of those folders is going to be massive, a huge rabbit hole. And this is where Java packaging comes in, right? I want to only look at Tinder code. I go into COM, I need to go into Tinder. And this is all the code from Tinder. Everything else is libraries they are using, right? For example, this is stuff from stock Android they're using, but they also are integrated with Facebook, and so they need to include a lot of Facebook code inside their own APK, right? This is why APKs are so large, because you include all the libraries you use in a single package. It's kind of static compilation, for normal operating systems. Now, as soon as you open this, I'm not sure if Tinder is obfuscated or not. I don't think so. I'm going to look at, for example, let's look at matches, right? I don't know, trigger, right? Those are the components. And when you click on a single file, here you will see that it is the compilation on the right screen, right? You can see it's the compiled bytecode because it's not perfect, right? Here, for example, it could be that this is just data. It could be that JADX is mistaken. It's part of the bytecode. But you can see that most of the code is surprisingly readable. Like, look at this. This looks actually normally written Java, right? However, as soon as you scroll a bit, you see that there are some JADX comments saying, look, I had to change this. And for some stuff, variable names are not kept. Like, for example, this is a variable name auto-assigned by JADX because it doesn't know. Sometimes in the process you lose this kind of information, right? This is going to be very common, and I probably won't be able to find an example of this because probably it's simple app, but it's not uncommon to see instances in which JADX fails the compilation and just dumps the DEX bytecode. It is rare, but if an app is obfuscated, this is going to happen, right? JADX also gives you a lot of very nice features, right? For example, I can right-click on something and go to the declaration. But even better, find the usages of this, right? This is probably not going to terminate. I'm not going to wait for this because the APK is huge. But this is so nice to have. When you're reversing an Android app, usually you want to find, maybe you think vulnerability is somewhere, and you want to see, okay, how do I trigger this? What is the path I need to take as a user to trigger this vulnerable piece of code, right? If you're interested in all of this, we're going to go more in depth into in the exercise session on Wednesday. We have some very small Android CTF challenges in which you need to reverse the app, understand the logic, and actually find the flag, and we're going to show a bit how it works. So if you want more details, just come on Wednesday or play around yourself with it. Okay, cool. So let me now put this back to where I was. Here. Okay. Now, here it's another important part of the lecture where we talk about mitigations. So we saw how the bug reporting process goes, how normally people look for bugs by decompiling the apps and analyzing them. It's very important, though, the measures that Google and other vendors take to prevent vulnerabilities to do too much damage. Mitigations are a way to stop turning bugs into vulnerabilities, right? How does it work? It works by using many security measures, in depth, one on top of each other, to prevent a small issue to become a large issue, right? So we already saw an example of one, right? The fact that each app is a single user. So if I find a vulnerability in an app and I get code execution, for example, I can only steal the data of that single app. I cannot really translate to another app. To do that, I need to bypass the security boundary that the kernel enforces, which means exploiting the kernel, right? So I need a chain of 2 bugs at least to move to another app, right? Unfortunately, this is way more common than you might imagine, right? Being able to exploit the kernel, right? Here there are 2 talks, if you're curious about some incidents for how this can happen, from Black Hat USA. If you're curious, go and watch them. Another measure that Android is using, if you remember from previous lectures, there was a difference between discretionary access control and mandatory access control. One is much more fine-grained. One lets you explicitly state what each process can and cannot do, right? We made SE Linux as an example. And in fact, on Android, SE Linux is present and enforced, right? There is a deny by default policy, and for every domain, which is a group of processes or actors, Android specifies exactly what each one of those can do, right? There are so many of those. There are at least 60 in your phone, probably more, but every app follows this. If it's a manager, they have a special one, but by default is very, very restrictive, right? Next mitigation. We have something called memory tagging extensions, right? Now, for who played around with C and knows what pointers are, and use the debugger, they probably noticed that the upper bits of a pointer are always empty, right? They're never used. Usually a pointer is 64 bits, you only use the last 48, more or less, it depends, right? Now ARM decided to make use of those unused bits by storing a tag there. And this tag encodes the information of what memory region can this pointer target. This is an extreme simplification, but more or less this is what happens. And every time you use this pointer to write or to load, right, the CPU in hardware will actually check, was this allowed or was not allowed? Does the tag match which region of memory this pointer is targeting? And if it's not, it's going to cause a crash, right? So what is this preventing? Maybe you have a memory corruption vulnerability, and an attacker managed to corrupt a pointer and wants to write to another zone of memory, right? This will stop that, right? The attacker now needs more. The attacker now needs to know what is the correct tag to write there. So it's a step more in the exploit they need to go through. They need to bypass one additional measure, right? So now they need another bug, right? So with this, now your chain of bug from 2 became 3, right? This is how mitigations work. You put one on top of each other until the exploit becomes very complex and very expensive, right? Another one is Scudo. Scudo means shield in Italian. If you go into the details, you'll see that it's not that much of a shield, but Android has a slightly better version of malloc, right? Malloc is how you allocate memory in C. The improvements are that the allocations are randomized, so if you have a buffer overflow, now suddenly you don't really know what you're overflowing, right? You need another bug to know. There are some guard pages that prevent to have heap overflows across memory ranges. And basically, to avoid going too much into details, before each chunk of memory that you allocate, there is a bigger header compared to malloc that stores more information about if this was freed and in which chunk size and so on and so on. So it's a little bit harder to perform a double free or a user after free. Now again, keep this in mind. This was exploited countless times, right? It doesn't prevent exploitation, it just makes it a little bit harder, right? And this was enabled since Android 11, the ARM-MT since Android 12, in Android 13, 14, 15 there are more security mitigations. We could go on and on and on, there are so many. In fact, nowadays more or less for a full compromise for a device you need 5, 6 bugs, one after the other, all chained together to get complete control, right? Which means becoming root. Let's do another break, and then we're going to conclude. We're almost done today. It is, so the last part of this lecture, I answered because as of now we did the theory, which is very important to know the theory behind it, in case you go to, I don't know, you have an interview question about Android and stuff. But I also wanted to tell you about the practice, right? So I've been doing some research on Android, and I've seen some things, good and bad. I want to tell you about my experience. What do I think about actually the state of Android security, right? So the first thing I want to touch is what probably everyone came here for, which is this. Right, of course. Before I'm going to tell you what is my opinion, I want to know yours, right? I want to know yours, of course. Who thinks Android is better, security-wise, safety-wise? Imagine you are CEO of a company, right? You hold some very important information, but you need a mobile phone for your work, for sure, right? What are you going to use? You're going to buy an iPhone? You're going to buy an Android? Right? Personal opinion, please come forward. Give me some opinions. One is fully open source, fully. Well, we saw, not really. But the other is completely closed source, right? One is.
How your company should interact with Apple? Because if you have much interaction with Apple, I would prefer not to buy iOS.
If you have a lot of interaction with Apple, you should not buy an iPhone. Okay. Because you are liable to, maybe they get very angry. You shouldn't make enemies with a lot of money. Correct, yes. It's a good point. Imagine your company is smallish. You don't risk being threatened by Apple. Just on a technical point of view. Yes? More iOS, why?
Because like also for the applications, like it's, if I'm like not the expert as a user, I have more, I have to follow the workflow in the file. And so like maybe I don't install it.
That is true. There is a good point, also linked to this, that the App Store on iOS is much, much more controlled. And for example, to publish an app on iOS, a human, someone at Apple, will verify that the app, we will need to get approval by a human. In fact, it takes like 2 weeks to publish an app on App Store. It's very expensive. This is why. On the Play Store, instead, it's on automatic. There are some checks, but they run in half an hour, right? It's very cheap to publish app on the Play Store. This is why it's much harder to find malware on the App Store than on the Play Store, right? You cannot install your own app on iOS, for example. Your own, by I mean you cannot just download an APK online and install it, right? Maybe it's going to change in the future with some Europe regulation, but nowadays you can't, right? So it's kind of harder to install malware, but on the other hand, you're way more limited in what you can install, right? Apple needs to approve it. What about the closed versus open source? What do you guys think? Is open source better than closed source for security?
That depends on, for example, if you don't spend money on security of your open source project, you don't buy some reviews and so on, it will be even less, it will be much less secure. But if
might be more secure. Why?
Because
Imagine I follow the same rules and I have the same mitigations. Only one is visible by everyone, the other one is not.
so the problem is it's harder to guarantee that all the procedures were followed by creator of proprietary code, because he wouldn't publish all the information about these investigations.
So what you're saying is open source allows the option to have anyone to look at it and to spot problems. Maybe you followed the wrong...
And all the reviews of this code are also published. So we can view how security of this code is maintained. And with proprietary code, we can't view how it's maintained.
And this is a very good point, right? It's auditable, open source code, right? By other people and by yourself. And for very popular projects, you kind of trust on the community to audit it for you. For example, Linux, the kernel, is open source. It's somewhat safe, right? It's not riddled with bugs because so many people look at it, right? However, a lot of people do the arguments in the opposite direction. They say, okay, the fact that it's open source makes it so much easier to find bugs, incredibly easier, right? And on some level, this is true, right? The fact that audits are public also helps attackers to find variants of bugs, right? So it's not super clear, right? If it's, I would ask you, what's safer, Linux or macOS, right? It depends, right? There's not a clear answer, right? The debate is very, very large and intense, as you can probably imagine, right? There is not a clear answer. Also, the answer on who is the most popular kind of depends on the geographic region. An interesting data point is in richer countries. You guys are students, so maybe you didn't realize this yet, but in Switzerland everyone is full of money, right? In fact, iOS is the most popular choice, right? If you go to a more reasonable country, Android has absolute market dominance, right? You cannot see, but it's like, 95%, right? What are the strategies of, we see this is just popularity though, what about security, right? What are the strategies of the two companies? Apple is extremely closed, right? You can only run apps that come from the Play Store and that were vetted by Apple, they were signed by Apple, and they are making it incredibly hard to jailbreak your device, to have root on your device. They don't want you to have control of your own hardware, because they say the user can mess up. We don't want this. We want to have a good, solid brand name. Apple means security, and people should have trust in that. Because if a user jailbreaks his device and then gets exploited, maybe it's bad reputation for us, right? Also, how did they make it so hard to jailbreak all the iOS devices? They hired half of the jailbreak hackers. So many of them now work at Apple, right? And they really helped to make the device more secure because they were the hackers in the first place, right? Another advantage they have is that they were the first on the market, right? So they got the initial smartphone hype, right? And also they control the full chain. They don't have the fragmentation issue. They make the hardware, they make the software. It's not fragmented, right? There are different device versions, but it's a single family of devices. It's going to be very easy for them to update the latest iPhone to the latest security patch, right? They don't have this problem that Android has, right? Don't underestimate the benefit that they have by being the first to market, right? In fact, Google didn't have this and adopted another strategy, right? To get popular, Google said, okay, look, I'm going to let people customize the software. Everything is open source, I'm going to let it customize. What is the advantage? The advantage is commercial, right? Because they knew that brands like Verizon, like Salt, They want to have a custom phone. They want to sell you a branded sold mobile phone, a branded AT&T mobile phone, that you power it on and you have the AT&T logo. Android lets you do that, right? Vendors like this, right? And this is why Android also managed to catch up with iOS, right? It can run on many different devices. You don't need to control the hardware. It's very, very much customizable and open. They let you install apps you download from the internet, APKs. Developers have much more power. And they, to some extent, they let the user jailbreak their own Android device by design, right? The strategies are very much opposite. Right? It's actually easy to tell, this is the right choice. Right? Also because most of the decisions were made from an economical point of view, not from an ethical point of view, right? Another important point to note is that they are converging. Android is really taking the path that iOS took a long time ago. Android is very much different than how it was 10 years ago. 10 years ago, running a custom ROM, a custom Android, was much more popular, at least in my friends group. And nowadays, jailbreaking Android devices is becoming incredibly much more cumbersome, right? For example, Xiaomi requires you to log into their website to unlock the bootloader, which is incredibly user hostile, right? But they're not the only ones, right? They see the benefit in not letting the users fiddle with the low-level stuff, right? We made the example again. The Play services are very hostile against jailbroken devices, right? So the difference is more or less this, right? One is open, one is closed. There is this thing called the Kerckhoff principle that says, talking about cryptography, but it can be applied to any system, that it should be secure even if everything about the system is known, right? Even if you can read the whole source code, it should still be safe. Now, it is a principle because it's not always true. Otherwise, it would be a law, right? Now, to get more in depth into what is the most secure, to explain it, I would like to talk to you guys from the money point of view, from the economical point of view, right? And here we want to talk about the mobile exploit market. So, before we talked about the bug bounties, a security researcher can make money by reporting vulnerabilities. They can make much more money by selling exploits to a government, right? And the government will not patch. The government will write an exploit based on it, right? This is probably almost for sure, how Pegasus built their own series of spyware, by buying exploits, right? And it's interesting to know what is the price of those exploits. How much does it cost for a government to exploit someone, right? This was in 2019, a website called Zerodium. The font is small, but I'll tell you, the top row was a payout for Android FCP. FCP means full chain with persistence across reboots. 0 click. The user doesn't need to click on a link. The user must just be connected to the network. You have the mobile phone, you send an SMS, exploited, right? Without the user opening it. This was worth $2.5 million, right? This means a chain of 5 to 6 bugs. Remote, probably leakless, very, very incredibly hard to develop, but there is evidence of those exploits in the wild that have been used, right? The row before, for iOS, same thing, full chain with persistence, 0 click, 2 million, right? There were also huge bounties for just WhatsApp, because of course it's the juiciest target on someone's phone. All the chat logs, or iMessage, that was $1.5 million. This was 5 years ago, right? In the last 5 years, they more than doubled the prices of this. For Android, 0 click, full chain, that's 5 million. For iOS, this is 5 to 7 million, right? This is from a different, let's call it broker. Those websites buy the exploits from you, and then they sell it back to governments and stuff. If you're thinking about this, you will get scammed by those websites, right? You will get your money stolen. Don't sell exploits to governments because, it will. You will get people in trouble, if not killed or worse. So don't do this. And there has been many stories of those companies not really paying exploit developers, and so on and so on. But this is what they officially advertise. Probably the government pays more than that to them to have the exploits, right? An important thing to note is when they are talking about Android, we see that the prices are similar, right? Android AIS, that's the order of magnitude, right? Millions of dollars, right? However, when they're talking about Android, they're not really talking about the Android. They're probably talking about a few selected devices. They don't list the details here. Of course, you need to go write them an email and go into communication with them. Probably they're talking about the Google Pixel and a few other devices which are considered very safe, right? Most of the Android devices are tragic, okay? Samsung, for example, which is considered not so bad normally, it's incredibly brittle, right? A full chain for a Samsung device 1 month ago for COM402 is a conference in which they award big bug bounties to developers, not for selling exploits, but it's an actual bug bounty, and usually they give a lot of money, but for a Samsung S24, the latest model, they only offered $50,000. Which looks really low for the amount of time you need to put to write. I don't know if you can see, but they used 5 different bugs, right, to get a full chain on this the latest Samsung device, and they were awarded only $50,000. This means that they didn't spend a lot of time on this to find those 5 bugs, and who knows how many more, right? Another important data point to see this is Celebrite. Who knows what Celebrite is? Yes, what is that?
It's a tool that police forces supposedly use to unlock devices that they get from people who have the data.
Yes. So Celebrite is a company that makes this device. It's a very big device. You can buy if you're a law enforcement agency, if you're the police, right? And allows you to plug a device via USB. This big brick is filled with 0 days for most devices and allows you to dump the file system of a phone. Unlock it and dump everything. Remember that basically all phones nowadays are encrypted by default, right? So they're able to unlock, decrypt them, and give the law enforcement the evidence they need to send whoever to jail. This table is incredibly small. You cannot read it. You look at it later from downloading the slides. The only important thing you need to see is that the last row, this table comes from a leak. It's not publicly available. Celebrite didn't share this. This was part of their package to sell to I don't know which police agency. And it's from last year, right, when the iPhone 16 did not come out. And this is the table for the iPhone support. In the last row, we have the iPhone 15 Pro or Max. It doesn't matter. And in the vertical, we have the iOS versions. And you can see in the last 2 columns, which are the iOS for iPhone 15. They would support something called AFU, which is after first unlock, which means has the phone been turned on and unlocked at least once. If this is the case, it means that the encryption key is somewhere in RAM, right? And then they can dump the whole file system, right? So for the police is almost not a problem dumping the file system of your iPhone if they purchase one of those Celebrite. I have no clue of the price that this is, costs. However, it's important to note you require physical access to the device, right? And it needs to be turned on. Keep this in mind. If you're in trouble, turn off your phone. Let's look at the Android part of this. So in the leak, they didn't leak the whole slide deck. They only leaked the relevant part for Pixel phones, so we don't have information for other phones. I'm going to assume that the other phones are much more unsafe because Pixel have much more support. They're from Google and so on. And here we see that on Pixel phones, they actually support before first unlock, so even if they're turned off, right? On standard Android OS, except there is a big difference. What if you're running Graphene OS, right? Now here there is some marketing speak in they say before first unlock, yes, up to late 2022 security patch, which means is that if your Graphene OS installation is 2 years old, then they can still dump it, right? Which means they do not support the latest version, right? Not even after first unlock. So Graphene OS actually resists Celebrite. What is Graphene OS? It's a custom Android ROM. It's considered one of the most hardened ones, right? It's made by a group of people who are mental about security and privacy. They disable an incredible amount of features, right? I'm actually very surprised someone is running this because it makes it a bit harder to use, but the guarantees it gives you are crazy, right? I listed here just a few features, but if you go on the website, there are pages and pages of the stuff they do to mitigate exploitation, right? And it's really well done. It's so well done that, in fact, many of the measures they take, they then get merged into mainline AOSP, right? So you have this Android distribution, which is the forefront of mobile security, basically, right? On the other hand, on iOS, you can also improve the security of your device. Probably you guys have heard of one of the latest additions to iOS 15, which is this lockdown mode, this super strict mode you can enable, and it disables a bunch of stuff. It really reduces the attack surface that you can that is available, right? So for example, JavaScript is not JITed anymore. You don't have any of the fancy iMessage features. The IPC mechanisms are really toned down, and so on and so on, right? Another example of what to pick is we can look at what the CEO of CEOs is running, the US president. Of course, he needs a phone, and he needs Twitter installed. Well, in this case, probably Truth Social. Anyway, last month, Donald Trump switched phone, and what is running now is a custom Android distro from Green Hill Software. Almost nothing is known about this. We only know that it's a hypervisor-based Android distribution. Probably means that each app is running in its own virtual machine, likely, but we don't know the details nor the price. However, it's a safe bet that this is a pretty safe Android distribution, right? So in conclusion, right? Mobile security is not exactly the same as on a laptop, right? The incentives for attackers are different. The trade-offs you need to make are different, right? You want your phone to be usable, but you really care about security, right? Between Android and iOS, there is no clear winner, right? On Android, you have much more freedom to choose. You can make an incredibly safe phone. You install Graphene OS, it's going to be very safe, right? However, if you keep your stock Samsung, it's going to be incredibly more unsafe than an iOS, right? A stock iPhone gives you good guarantees, right? It's reasonably safe, but it doesn't let you play around with it, right? So you kind of have this choice. On Android, you're free to turn it up to a notch or turn it down. iOS, no. You are basically walled into what Apple defines as security, which is still pretty high, all things considered, seeing the payouts. But it's comparable maybe to a Pixel phone, right? Biggest challenges are the fact that software comes from a lot of places on Android. Fragmentation is probably the biggest challenge of them all, right? The difficulty in coordinating all those developers, all those companies needing to put their code on a single device. And yeah, the fact that devices are often outdated and there is very little check on this app market also contributes. If you want some practical experience, come to the exercise session on Wednesday and we'll have a few challenges for you. And thank you very much. We are done for today.